Okay, so in this video, we are going to be putting together everything that we've learned about in section 4.1 and 4.2. Okay, so the nice thing about this section is we are going to be able to use Desmos to verify all of this information, but it is going to help us determine what part of the functions make certain things happen in the graph. Okay, so step number one is we're going to identify our domain. Then we're going to figure out if we have any symmetry. So remember, we have odd symmetry when it's symmetric about the origin, like for instance, y equals x cubed. If we have even symmetry, it's symmetric about the y-axis, so that would be like y equals x squared. If it has neither symmetry, that would be like y equals x cubed plus x squared. We are going to find our first and second derivative. And from the first derivative, we are going to locate any critical points. From the second derivative, any inflection points. And then we're going to actually find all of the intervals for which our function is increasing, decreasing, concave up, and concave down. We're then going to identify any of the extreme values and inflection points, locate any of our asymptotes, and determine our end behavior, find any of the intercepts, and then graph. Okay? All right, so let's start with this first example. So we are given information about our first and second derivative of our function, which is continuous on the interval of negative infinity to positive infinity. And we are going to use a number line to summarize all the data together and then sketch a possible graph. Okay, cool. So first, let's make the number line. So in this case, I'm noticing my interval, the first thing that they give me goes from negative infinity to 0, then 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 8. So pretty much 0 through 4 are my numbers. 0. Okay. So what I'm going to do, and I'm going to do this for each one of these examples, is at the top here, I'm going to deal with the first derivative. And actually, let me scoot that over a little bit. Okay. Okay, there we go. So at the top here, I'm going to deal with the first derivative. And then here at the bottom, I'm going to deal with the second derivative. Just personal preference, how I like to organize this. Okay. So they told me from negative infinity to 0, so that's this first section here, my first derivative is less than 0. Since my first derivative is less than 0, that tells me that that is decreasing. Okay. And my second derivative is greater than 0, which tells me it's concave up. Okay, so I got that from here. Did this one. Okay. All right, let's do the next one. So in this case, it is greater than 0 for the first derivative, which means I'm now increasing. And I am still greater than for my second derivative, so I'm still concave up. All right, the third one. Okay, greater than for my first derivative, so I'm still increasing. But now my second derivative is less than 0, which means I'm concave down. Next, we have first derivative and second derivative are both less than 0. So that means I am decreasing and concave down. And next, we have less than 0 for first derivative and greater than 0 for second derivative, which means I am decreasing but concave up. And lastly, I have both greater than 0, which means I am increasing and concave up. And I somehow managed to lose the 4 that was there. Okay, so what this is telling me is, since wherever I'm changing from, let's do this blue, changing from decreasing to increasing, that's going to be a local min. Okay, so I have a local min here at 0. Okay, local. And I also have a local min here. Okay, and then when I'm going from increasing then decreasing, that's going to be a local max. So here, sorry, that's a little messy. Okay, and then the other thing that I want to notice is when I'm switching from concave up to down or vice versa. So when that happens, we have an inflection point. So I'm going to have an inflection point here at 1. And also at 3. Okay. Okay, so I'm going to add another page so that I can sketch the graph on there, so I give myself enough room. Did that work? I don't think that worked. Okay. Oh, all right. It's thinking. Oh, okay, it did work. Good. All right. So let's go to the next page. Okay, so I'm gonna draw my graph. And I'm gonna put 1 through 4 on my x-axis. Okay. So things to keep in mind. We have a local min at 0. And I know that we need to be decreasing and concave up, and then increasing and concave up around the 0. Okay, so I'm just going to put a dot here for my local min at 0. I need to have my function be decreasing and concave up from negative infinity to 0. So it could be something like this. And then it is increasing and concave up on the interval from 0 to 1. So it could be something like this, okay? And then from 1 to 2, it's going to be still increasing but concave down. Okay, so increasing and concave down. All right, so we have that now. And then from 2 to 3, we have decreasing and concave down. Okay, so decreasing and concave down. And then from 3 to 4, we're still decreasing but concave up. And from 4 to infinity, we're going to be increasing and concave up. Okay, so it'd be something like this. All right, so remember, this is just a rough sketch. It's not the only possible answer, but let's go ahead and label everything that we had. We had a local min at 0, and another local min at 4. Okay, so I'm gonna make like a little key for myself. We had a local max at 2. Okay. Our inflection points happened at 1 and 3. Okay. And then I'm just going to label where we were concave up and concave down. So concave up, concave up, concave up, and concave up. And then we'll do concave down. Okay, so that's pretty much the gist of it. So now they gave us the first and second derivative values for that. So when we're starting from the beginning, we're actually going to have to find all of that. All right, so let's go ahead and knock out our first example. Okay, so we're going to run through our guidelines. So first, we need to figure out what the domain is. Okay, so in this case, are there any restrictions that you can see? And the answer is no. So this domain is continuous all the way from negative infinity to positive infinity. Okay. The next thing you're gonna check is your symmetry. And another way to check without using your calculator is when you plug in negative x for all of the x values, if you get the positive original function back, the exact same thing, then it is even. If you get the complete opposite of that, it's odd. And if you get something totally wonky, it's there. But in this case, I'm noticing that my exponents are both odd, so 3 and 1. So this is odd, which means it's going to be symmetric about the origin. So essentially, if I do a 180 with the graph, it'll look exactly the same. All right, next we are going to find our first and second derivatives. Okay. So my first derivative, we're going to get x squared minus 400. And my second derivative, we will get 2x. Okay. All right. Step number 4, finding our critical and our inflection points. Okay, so for our critical points, we're using our first derivative. So we're going to set that equal to 0. So we're going to get x is going to be positive or negative 20. All right, and then for our inflection, we're going to set our 2x equal to 0. So x equals 0. Okay. Now, step number 5, we're going to make our number line. So I'm going to do this just like I did the first example. I'm going to go to the next page so it doesn't get super smushy. Okay, so negative 20, 0, positive 20. All right, so just like I did the first example, I am going to do my first derivative at the top and my second derivative at the bottom. Just keeps me organized. Okay, so when I'm picking my test points, you don't necessarily care about the actual value, you only care about the sign of the value. So if I start with the first one, I'm going to pick negative 21. So what I'm going to do is I'm going to plug in negative 21 to my first derivative of x squared minus 400 equals 0. And I'm going to see if the answer is positive or negative. And in this case, it's positive. So since it's positive, that tells me it's increasing. Okay. And then I'm going to plug in negative 21 to my second derivative of 2x, and that is going to be negative. So the negative tells me that it is concave down. Okay. All right, so then I'm going to do a test point between negative 20 and 0. So I'm going to pick negative 10. And if I plug in negative 10, I'm going to get a negative. So I'm decreasing. And I'm going to get a negative, so I'm still concave down. And then I'm going to pick a positive 10 for the next. And positive 10 is going to give me a negative, so I'm still decreasing. And it is going to give me a positive, so I'm at concave up here. And last set, I'm going to pick 21. And 21 is going to give me a positive, so now I'm increasing. And 21 plugged into my second derivative is going to give me a positive, so I'm still concave up. Okay. All right, so from this number line, I can then identify my local max, my local min, and any inflection points. Okay, so we have a local max when it's increasing and then decreasing, so that happens at negative 20. Okay, there we go. Okay, so my local max is when x equals negative 20. And if I plug negative 20 back into my original equation, I can get the y coordinate that goes with that local max. Come on, pen. Okay. Oh, there we go. Now it's working. All right, so okay, come on. Guess my computer's not fully awake this morning either. All right, come on. I just want to make a 2. Okay, there we go. Negative 20. And if I plug in negative 20 to my original equation, I'm going to get 5,333 and a third. Oh my gosh. Okay, this is driving me crazy. Okay, so let's see. All right, negative 20 and 5333. Okay, and my local min, this is when I am decreasing and then increasing, so this happens at positive 20. And if I plug in positive 20, I will get negative 5,333 and a third for my y coordinate. And then my inflection point happens when I change from concave up to concave down or vice versa. So that happens at 0. And if I plug in 0, I will get 0 for my y. Okay. So step number 7 is we are going to figure out our asymptotes and our end behavior. So in this case, there are no asymptotes because I have no real restrictions on anything that happens with my domain. I'm not sure why I did that, but whatever. Okay. Asymptotes are none, and then come on. There we go. And behavior. So for our end behavior, what we're essentially looking at is we are looking at the limit as x goes to positive infinity and negative infinity, what our function is doing. So let's see. Okay, so still thinking. All right. So the limit as x goes to infinity and the limit as x goes to negative infinity. What is f of x doing? Oh my goodness, this is really bad. Come on, thingy, stop thinking. Guess I'll try with the pen again and see if that works better. All right. It's like everything is lagging. My internet's being slow today. All right, so as x goes to infinity, what is your function doing? So if we look back up at our chart for our number line, it's increasing in concave up. Okay, so that means as x goes to infinity, f of x is also going to infinity. Okay, and then if we look at the other end of the number line, it was increasing going from negative infinity to negative 20, which means as I'm going down to negative infinity, I'm decreasing. So f of x is going to negative infinity. Okay. All right, step number 8. So for step number 8, we're finding our x and our y intercepts. So this is when you set x equal to 0 and y equal to 0, and you solve. We already have the y-intercept in this case. From our inflection point at 0 for x, we also have 0 for y, so it's 0, 0 for your y-intercept. Oh my goodness. Sorry, guys. That's so bad. Okay. And then for your x-intercept, you're going to set your original function equal to 0 and then solve. And you'll get 0, just like we got for the inflection point, and you'll also get that x is the other x-intercept is minus the square root of 1200. Okay. Oh, and then we just need to graph it. So you probably want to graph these ones in Desmos rather than your handheld calculator, just because some of the windows are going to get a little weird that you would have to go to. Okay, so there is our graph, and that matches everything that we've just done. So yay! Okay, so here's our next example. So the first thing that we're going to do is we're going to find our domain. Okay, so in this case, I have a fraction, and since I have a fraction, I know that I'm going to have some restrictions on my domain because I can't divide by 0. So domain. Okay, so what I'm going to do for this is I'm going to set the denominator equal to 0. And I'm going to solve. And when I'm doing that, I'm going to end up with x equals plus or minus 1, which tells me that my domain cannot include plus or minus 1 because then it would have 0 in my denominator. So we could then write our domain is as follows. We have negative infinity to -1 and -1 to 1 and 1 to infinity. All right. The next thing that we're going to look at is our symmetry. And this, we're going to focus on the numerator in this case, and the numerator is odd. So this is odd. Okay. Number 3, we need to take the first derivative and the second derivative. Okay, so this is going to be using the quotient rule. So for my first derivative, my low is x squared minus 1. Derivative of the low is 2x. My high is 10x cubed. Derivative of the high is 30x squared. Okay, so we're going to do low d high minus high d low, draw the line, square the low. So if I do that, I'm going to get okay. So 30x squared times x squared minus 1 minus 10x cubed times 2x all divided by x squared minus 1 squared. All right, so now I'm just going to simplify this. So first, distribute what I can. All right, and we're going to combine our like terms. So we're going to end up with minus 30x squared. All right, and then I can actually factor out something. And the reason why I'm going to factor it out is so that we can easier find our critical points. Okay, so I can take out a 10 and an x squared from the numerator. That's going to leave me x squared minus 3, all divided by. Now, when I do my second derivative, I'm going to use this. I'm not going to use this because then I would have to do the product rule and the quotient rule at the same time, and that would be crazy. But this is going to help me find my critical points. Okay. We found the first derivative. Now let's find the second derivative. And remember, I'm going to be using the 10x to the fourth. I'm not going to be using the factored form to find the second derivative, just because it will be easier to not have to do the product rule and the quotient rule. Okay, so we are going to need to do the quotient rule, and we actually also are going to end up having to do the chain rule as well for the second derivative. Okay, so let's see. So we have our low, which is x squared minus 1 squared. And so we're going to end up needing to do the chain rule for this. So to find the derivative of just the low. So u is going to be x squared minus 1, what's inside my parentheses. The derivative of u is 2x. And u squared, the derivative will be 2u. So essentially you're going to be multiplying 2u by 2x to get the derivative of the low. So the derivative of the low is going to end up being 4x, because 2x times 2 times x squared minus 1. Okay, now my high, I don't know what I just clicked. I clicked back. Okay, my high was 10x to the fourth minus 30 x squared, and the derivative of that is going to be 40x to the third minus 60x. Okay. So now that I have all of that, let's go ahead and do the low D high minus high D low. So let's see. All right, so we're going to have x squared minus 1 squared low times D high minus high put this in parentheses, D low all divided by x squared minus 1 squared squared. All right, it's getting a little crazy. Okay, so essentially one of the things that I'm noticing is that both the low D high part and the high D low part have an x squared minus 1. So I'm going to actually factor that out in the numerator. Okay, so that's going to leave me with 40x cubed minus, ooh, that's messed up. Okay, so this multiplied by the x squared plus 1 that I have left over because I can only factor out one of them. Minus and I'm going to go ahead and distribute the 4x to the 10x and the negative 30. So 4x times the positive 10 is going to give me, because I'm minusing, negative 40x to the fifth. All right, now you got to be careful with the 30 because it's a negative 30, but you're subtracting it. It's going to end up being a positive 30. And then 30 times 4x is going to give me 120x cubed. No, not cubed. 120, yes, it is x cubed. X cubed. Okay, what did I forget up here? I think I forgot something. Yep, I did. I forgot my x squared right here. Okay, all still divided by x squared minus 1 to the 4th power. Okay, so since I factored out the x squared minus 1, I can actually get rid of one of them in the numerator and the denominator. Okay, so that means this essentially is going to go away, and this is going to turn to 3. Okay. All right, and then I'm going to go ahead and FOIL out this first term as well. Okay, so now I'm going to have 40x to the 5th minus 60x cubed minus 40x to the 3rd plus 60x minus 40x to the 5th plus 120x to the 3rd, all divided by x squared minus 1 to the 3rd power. Okay, then from here, I can combine some like terms and simplify, and I'm going to end up with 20x cubed plus 60x, all divided by x squared. For some reason, 2 is very difficult for me to write with this pen. I wonder why that is. All right, and then I am going to factor this as well to make my life just a little bit easier for when I'm finding my inflection points. So I can take out a 20x from the numerator, and that's going to give me x squared plus 3 left over, and x squared minus 1. See what I mean? The 2's, it's difficult for me. Okay. So now that I have that, I'm going to find my critical points and my inflection points. So I'm going to actually add another page here. Because I'm just running out of room like crazy. Okay, so step number 4 is critical points and inflection points. Okay, so remember your critical points, you're going to take the, in this case, the numerator of the first derivative and set it equal to 0. So the numerator of the factored first derivative that we had was 10x squared, and then so I'm going to equal that to 0, which is going to give me x is 0. And then we also had in the numerator x squared minus 3. So this is the first derivative that I'm using. So I'm going to add 3 to the other side, and so I'm going to get x squared equals a positive 3. And then I'm going to take the square root, which is going to end up giving me x equals plus or minus the square root of 3. Okay. All right. Next, we have inflection points. Okay, so we're going to now take the second derivative numerator and set that equal to 0. So we had 20x, and so I'm going to get 0. And now this second part, this is going to be a little weird, right? What's going to happen here? Hopefully you're telling me that then I would have a negative under my radical, and then I'd get imaginary numbers. So we are not dealing with that mess. No, no, no. Okay. All right, so now we're going to make our number line. And what I want you to do is I actually want you to pause the video after we set up the number line. Okay. So the smallest number that I have is the negative square root of 3. And then the next number I have is negative 1. And remember, we have negative 1 coming into play because that was a domain restriction. Followed by 0, positive 1, and then positive square root of 3. All right, so I'm going to give you your test points, and I want you to plug them into the first derivative and the second derivative. and I want you to see if you get what I get, okay? So your test point for smaller than -3 is going to be -2. Your test point for in between -3, square root of 3, and -1 is going to be -1.5. Your test point in between -1 and 0 is going to be -1/2, -0.5. And then we're going to have a +1/2 and 1.5 and 2. All right, so plug into the first derivative, see if you get a positive. If you do, it's increasing. If you get a negative, it's decreasing. And then you're going to do the same thing with the second derivative. So pause now and do that. Okay, did you actually pause? Should I trust you? Okay, so I got positive, negative, 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 positive. Okay, so that tells me increasing, decreasing, 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 increasing. All right, now let's do concave up or down. I got negative, so down, negative, down, positive, up, negative, down, positive, up, and positive, up. Okay. Okay, so what does this tell me? This tells me that I have a local max at the negative square root of 3, and I know that because I was increasing and then decreasing. So insert another page. Just write too big. Did it work? Nope, it's still thinking. Okay, part 6. Okay, so my local max is at negative square root of 3. And if I plug that into my original equation to get my y coordinate that corresponds with that, I'm going to get negative 15 square root of 3. Okay, we have a local min, and this is where my function was decreasing and then increasing, and that happens at the positive square root of 3. So local min, and that happens at positive square root of 3 and then positive 15 square root of 3. And again, I'm getting that number by plugging in square root of 3 into my original equation. I also have one inflection point, and that is at x equals 0. Now, you might be wondering why we are not including x equals positive or -1, because didn't we change concavity there? And the answer is, yeah, we did change concavity there. We did change from concave down to concave up at both -1 and +1, but is -1 and +1 in the domain? No, which is why we're not going to include it. Okay, so let's just write that out. Do not include x equals -1 or x equals +1 because it is not in the domain. Okay. All right. So step 7. Step 7 was our asymptotes and end behavior. Okay, so Our asymptotes are two vertical at x equals 1 and x equals -1. All right, and so when we're looking at our end behavior, we actually are going to look at approaching 1 from both the positive and negative direction, since we can't approach 1 because it's going to be doing two different things. So we're going to have to separate that out. Okay, so there are total 4 limits we're going to find. The limit as x goes to 1 from the negative, the limit as x goes to 1 from the positive, and then we're also going to do the same thing with -1. So limit as x goes to -1 from the negative, and the limit as x goes to -1 from the positive direction. Okay, so if I'm doing these problems here, as x goes to +1 from the negative direction, my function goes to -infinity. And you can do this with test points if you want to plug them in. You can also look at the number line that we made. Okay, 1 from the positive direction, f of x is going to +infinity. -1 from the negative direction, we're going to -infinity. And -1 from the positive direction, we're going to +infinity. Okay, and then the last thing that we're going to do is we're going to find our intercepts. And to find our intercepts, we are going to set the numerator of our original equation equal to 0. So the numerator of our original equation was 10x cubed. And if we solve that, we're just going to get x is 0. So in this case, our intercepts are 0, 0. Okay, so you can verify all of this information we just found by typing this into Desmos. And if you do so, you will get a graph that looks like this. Okay, so we got our asymptotes at -1 and 1. We actually also have an oblique asymptote, but don't stress out about that one. Local max, local min, inflection point. So there you go. Okay, so there is one more example on here. So let's go ahead and do that one. My cat is sitting on my lap. Okay, so now for this problem, we could do the product rule, but we could actually just distribute, and that will probably be a little bit easier than doing the product rule. So that's actually what I'm going to do first here. Can you hear her purring? She's so loud. Okay, so if I distribute the 1/8 x to the 2/3, I'm going to get, ow, Chloe, 9/8 x to the 8/3 minus x to the 5/3 minus 2x to the 2/3. Well, why is x so... Didn't mean to make him be an exponent. Okay, 2x to the 2/3. Okay, so first, let's think about the domain. And are there any possible restrictions that I could have? And the answer is no. which tells me my domain is all real numbers. Negative infinity to positive infinity. All right, let's think about symmetry. What do you think? Odd, even, or none? If you said none, you are correct. There is no symmetry for this. All right, number 3, derivative. Okay, first derivative, let's go. So I am getting 3x to the 5/3 minus 5/3 x to the 2/3 and minus 4/3 x to the negative 1/3. Okay, so that's kind of really messy with my fractions and stuff, right? So what I can actually do to make my life a little bit easier is I can factor out 1/3 x to the negative 1/3. Now, you're probably saying, Ms. Mack, how did you know to do that? It just takes practice. I pretty much picked it because the 1/3 is going to help me get rid of my fractions that I have going on, and the negative 1/3 is going to take care of the fractional exponents. Okay, so it's one of those things that just takes a little bit of time to get used to, and just trying to make your life easier. Do you have to make your life easier? No, you don't. But I mean, why would you not want to? Okay, so on the outside here, I'm going to have 1/3 x to the negative 1/3, and so essentially what you're thinking about now is 1/3 times what is going to give you back 3, and the answer is 9. Okay, and the other thing that you want to think about is when we are dividing, we essentially are subtracting our exponents. So if you were to do 5/3 minus negative 1/3, it would be actually 5/3 plus 1/3, which would be 6/3, which would be 2. Okay, and if you don't believe me, type it into the calculator. All right, so then here I'm going to end up with 5x, and then I'm going to end up with 4. So see how much nicer that is? Ooh, it's so much nicer. Now, when I take the second derivative, I am going to use the blue equation. I'm not going to use the brown one, but I'm going to use the brown equation to find my critical points. And let's just go ahead and do that part now. So we know that when x is 0, this is going to be undefined because this is going to end up needing to drop down, okay, because I have a negative exponent. Okay, so x equals 0. And then I can also factor this. So let's go ahead and factor that. We're going to end up with x minus 1 and 9x plus 4. And at the bottom here, we're going to get 3x to the 1/3, which is why x is not allowed to be 0. All right, so if I set x minus 1 and 9x plus 4 equal to 0, that is going to give me x equals 1 and x equals negative 4/9. Okay, so those are my critical points I'm going to need for step number 4. Okay, so that's step 4. I'm going to write that down. Okay, so now we still need to find the second derivative. I haven't done that yet. So I'm going to be using the blue equation. All right, so my second derivative is 5x to the 2/3 minus 10/9 x to the negative 1/3 plus 4/9 x to the negative 4/3. Okay, so now just like before, there's something that I can factor out of this to make my life a little bit easier. And it's actually going to be 1/9 x to the 4/3. Okay. Okay, so if I do that, I will be left with 45x squared minus 10x plus 4. All right, and then again, I can factor that. So I'm going to get actually, I don't even think I need to factor it. Nine x to the 4/3. Okay, so now we can find our potential inflection point. Okay. So again, we are not allowed to have x equals 0. Okay. So this is my inflection point. Okay. So the next step is we are going to make our number line. Okay. So did I insert another page? Yeah. Okay. All right. So step 5. All right. So we have negative 4/9, 0, and 1. Okay. All right, so I'm going to give you your test points again, and I want you to pause the video and try this. So for this first region, I did -1, then I did -0.2, I did 0.5 positive. I don't know why. Why is he like, he's like super stretched out. Silly 5. Ooh, that was nice. Okay, and then what did I do for the last one? I did 2. Okay, so plug into the first derivative, and if it's positive, put a plus. If it's negative, put a minus, and then plug into your second derivative. Okay, so hopefully you paused, and let's check your answers now. So I got negative, positive, negative, and positive. So that's telling me decreasing, increasing, decreasing, increasing. All right, and then the same for the bottom. Let's go. I got positive, 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 and positive. All right, so that's telling me the whole thing is concave up. It's concave up all the time. Okay, so step 6, We're going to identify the local min. All right, so we have a local min when we are changing from decreasing to increasing. So that happens twice. It happens at 4/9 and it happens at 1. So that is x equals -4/9. And if I plug in -4/9 to my original equation, I will get about -0.78 for my y. All right, and then I'm going to also plug in 1 to my original equation. And if I do that for my y, I'm going to get about -1.9. Okay, now this one, we actually don't have a local max. So we do have a point where our function is increasing and then decreasing at 0, but notice how it's concave up both times. So essentially, like, it's going to end up looking like, so it's concave up and it's still concave up. So we're getting like a little cusp or corner point here. So we have a cusp local max at x equals 0. Okay. All right. Next, we're going to talk about our asymptotes and end behavior. So in this case, we have no asymptotes, no restrictions. All right, now let's talk about our end behavior. Okay, so we're going to do the limit as x goes to -infinity and as x goes to +infinity. Now think about this. If we are going to -infinity, when we were coming from, where's my pen? Okay, so when we were coming here, it's decreasing, right? So that means it has to start up to come down. Okay, so if I go backwards, the backwards of decreasing is increasing. So as x goes to -infinity, my function is actually going to +infinity. Okay. All right, and then if we're looking here, after 1, it is increasing, and so as x goes to infinity, my function is going to go to still +infinity. Okay. All right, the last thing that we need to find are intercepts. And to find our intercepts, you're going to take the original undistributed equation, and you're going to set each of those pieces equal to 0. Okay, so for the first section, 1/8 x to the 2/3, if I set that equal to 0, I'm going to get that x is 0. So I have 0, 0 as an intercept. All right, now the other side is going to be a little bit more of a pain, because if you try to factor this, it does not factor. So 9x squared minus 8x minus 16. Okay, so when we have something that doesn't factor, what do we have to do? The quadratic formula. Yay. Okay, so negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, so if I simplify that down, this is a 9. It's just kind of looking like an 8. I'm going to end up with 8 plus or minus 8 square root of 10 all divided by 18. Okay, so hopefully you're seeing that, hey, I could divide that because they're all even. And I'm going to end up with 4/9 plus or minus 4/9 square root of 10. And if you wanted to, you could also even factor out a 4/9. So 1 plus or minus square root of 10. So there's my other x-intercept. Okay. All right, so now let's just graph it. And it's gonna look like bam. Okay. So always concave up, and we got our little